Well, welcome to Cooling Systems for Strata Owners. My name is Grant Lang. I work with RDH Building Science, and you might be wondering, why would RDH be presenting on heat pumps? You might be thinking of us as producers of depreciation reports and building enclosure condition assessments. But the reality is we have a much broader expertise and range of services. I, for instance, am an architect. I've been practicing for over 20 years now. And my training and experience give me an understanding of the interrelated nature of building systems, of buildings in their environment. And with my professional focus on the rehabilitation and renewal of existing buildings, it provides me with a really good understanding of what ill-considered, expeditious decisions by designers and builders can result in, and what we need to do to make buildings better. Most of my work is with stratas, so I'm very keenly aware of the dynamics of strata decision-making and strata's need to make the best use of what are typically limited resources, all things which play into the discussion we're going to be having today. Christy?
Yeah, good morning, everyone. So I'm Christy Love. I'm a professional engineer with RDH Building Science in our Victoria office. Now, what I'm bringing to this discussion is that I've focused most of my career looking at ways to improve the environmental performance of buildings. So energy efficiency, water efficiency, more recently, carbon reductions, climate resiliency. And I have a particular sort of interest in doing very practical research. So in the last several years, we've done a number of very detailed field studies involving retrofits to existing buildings that include heat pumps. So we've had the opportunity to really dive into how systems are designed, what kind of factors contribute to a successful project, and then how those systems actually perform in the real world. So just got some insights to offer there. So I'm not like a detailed mechanical designer. I do have some mechanical experience, but really it's sort of from that practical, really looking at how these types of systems are performing in the real world. Back over to you, Grant.
Simply said, what we're hoping to be able to provide you is an understanding of what the implications are of adding heat pumps to your building. Things that you might want to be considering as an owner. You might want to install a heat pump for their unit. And what things you might want to be considering as a strata corporation in buildings that may have owners that want to install heat pumps, or maybe considering heat pumps as a more general measure. So we're going to be speaking both about the specifics of heat pump technology and the implications for owners and strata corporations, as well as spending some time discussing some of the broader contextual issues that may be of significance for stratas planning in maintenance and renewals to their buildings. So why cooling? How does your building get hot? Why a heat pump? What is a heat pump? Some general considerations, how heat pumps fit in with other strategies, and planning for future climate and policy changes. So why heat pumps? I mean, here we are in the beautiful temperate coastal climate. It's not very often that we find residences with air conditioning or heat pumps. But I think everyone recognizes what that graphic on the right means. Was that heat event that we had early last summer. And it has resulted in the recognition that maybe we need to supplement our cooling strategies for our buildings. It's also an issue regarding the vulnerability of certain occupants, the elderly, for instance, who have difficulty in being able to handle hot climates. We saw, so it's also a safety issue in a sense, but it's primarily one of comfort, and it's related to climate change. We're going to be seeing more of these events and continued rise in in average temperatures. And so that's why people are asking for cooling. In terms of how your building gets hot, there's a number of different mechanisms that lead to your building getting warmer. But we're going to focus on one in particular, and that's the sun. The sun radiates energy. Some of it is heat energy, and that energy passes through windows and warms surfaces on the interior of the building, which in turn warm the interior of the building. That heat gets trapped inside the building. It also warms the exterior of the building. That heat gets transferred to the interior. So the sun is a primary source, obviously, during our summer season in heating up our spaces. And keeping that in mind, I'll hand it over to Christy.
Thanks, Grant. So why a heat pump? Well, heat pumps can be an efficient way to provide cooling and heating. Some people are possibly asking about them right now because they're seeing a lot of promotion around heat pumps, incentives coming from utilities. And the reason for that, just to provide that context, is that the province has commitments to reducing greenhouse gas emissions. And they see heat pumps as being a key technology toward achieving those targets. They're primarily focused on offsetting heating demand with more efficient equipment, as well as domestic hot water demand. But sort of the nice thing about many of the heat pump products that are available right now is that they'll do both heating and cooling. So you may not be able to get an incentive for a heat pump to just do cooling. You have to demonstrate that you're also offsetting heating demand. But that's kind of where the promotional incentives are coming from. So, and I wanted to also just contextualize the discussion in some of the requirements that have come out. So in the Clean BC roadmap, which sort of sets the province's strategy toward emission reductions, they're requiring by 2030 that all new space and water heating equipment will meet the highest standards of efficiency. And what they specifically mean by highest standards of efficiency is that all new space and water heating equipment must be a minimum of 100% efficient. So heat pumps, by their nature, will qualify. Something like a natural gas furnace or a natural gas boiler will no longer qualify. There are potentially some gas-fired heat pump products that may, but this is really driving a push toward electrification. And the sort of the heart of that is that our hydroelectricity grid is largely clean, or it's very clean relative to any sort of fossil fuel-based energy generation. Okay, so let's get into how a heat pump works. So a heat pump is a machine that moves heat using the magic of the refrigerant cycle. So in the winter time, the heat pump is absorbing heat from outdoor air in the case of an air source system. And yes, when the temperature is below freezing outside, a heat pump can still extract heat from that air, and it moves it via refrigerant to the inside of the house to heat it. In the summer, many heat pumps that are available now have a reversing valve, and they can reverse the cycle. They can then remove heat from the inside of the house and eject it outside. And what we like about heat pumps and many of the products that are available today is that they do this very efficiently. So there's a metric called the coefficient of performance that basically says how much energy out do you get for the energy you put in. So a heat pump requires electricity to run the compressor that compresses the refrigerant, which allows it to absorb heat, and then to run fans. So you have to put in a certain amount of electricity, but in the case of many heat pumps, you can often get for one unit in, you can get 3 units of heat out. So basically 300% efficient. That does vary by product, by type of heat pump, depending on the outdoor temperature. I'll come back to that later. But if you compare that to say electric resistance baseboards, those are considered to be 100% efficient. So for every unit of energy you put in, you get 1 unit of heat out. Your typical natural gas furnace will be anywhere between like 85 and 93% efficient, so always less than 1. So you can see why there's a big push to use more heat pumps. There are different types of heat pumps in terms of where they get their heat from and then how they deliver that heat. And when I say heat, I also mean like removing heat, so in that sort of cooling cycle. We're going to be talking mostly about air-to-air heat pumps because they tend to be most easily retrofit into like existing condo buildings and those types of buildings. And there are a lot of really good products available. So what those do is they take heat from the air and then they deliver it via air. So think fans. So there'll be some kind of a fan mechanism that's blowing over the coil that's either heating or cooling and then mixing the air in the space. Let me just get my pointer here. There we go. Air to water heat pumps may be appropriate in some situations, and there are increasing numbers of products that are available and suitable for residential type applications and for retrofits. So these are taking, again, heat from the air, but then they're putting that heat into some sort of water source. So in this case, it's a domestic hot water heater or a hydronic system. So you're transferring that heat into water, which can either be consumed through your domestic hot water system, or maybe it's distributed to a hydronic baseboard system or a hydronic in-slab system. Then there's water to air systems. So a chiller that's connected to a cooling tower would be an example of a water to air system. Typically more seen in large buildings. So where the chiller is circulating cooled water throughout the building. And then there are fan coil units in the zones that are blowing air over those coils to cool the air. And then you also have water to water or ground source heat pumps where you're using either the ground or a body of water as kind of a battery, and you're kind of borrowing energy from it and putting it back when you don't need it. Those tend to be more specialized, more expensive, and you kind of have to have the right sort of set of circumstance for a system like that to work. They also tend to produce lower temperatures. So yeah, more particular situations where those types of systems make sense. So I'm going to talk more about the air-to-air systems because I think they're most applicable to the types of buildings and situations that you're interested in. So let's zoom in a little bit. So there are a number of different types of air-to-air heat pumps. I'm going to talk first about distributed systems, which are systems that are fully contained within a suite. So your standard window rattler or wall box is an example of a distributed heat pump. It only does cooling, so it only works in one direction. They tend to be less efficient than other products that are available now. You are having to make a big hole in your enclosure to put the unit in, which has some issues. And again, you can't do any heating. You certainly wouldn't be able to get any incentives for doing this type of product, but technically it is a heat pump. Then you have your portable AC units, which are basically the same idea as the window unit, but you have a little bit more flexibility in where you put it. And the big gap in the enclosure is maybe a little bit smaller, but you have the same sort of limitations as the in-window unit. This is what we call a split system or mini split. Many of you may have seen these around. They're quite common. They're quite popular. They do tend to be quite efficient. So basically what they do is they separate the condensing unit, which is kind of the noisier part of the equipment, put that outside. And then you have an indoor cassette that has the evaporator and the fan that's sort of circulating the heating or the cooling. These are fairly straightforward to retrofit into buildings. You need to find a place to put the outdoor unit. It might be on a balcony. It could be on a rooftop. It could even be potentially hung on a wall. But you do need to find a space for it. And then you also need to run refrigerant lines between the outdoor unit and the indoor unit. And then the indoor unit is just recirculating air, running that air over the coil to either heat it or cool it. So these are very popular. They tend to come in capacities that are suitable for like condo style units. So they tend to be a good option, and these are incentivized. And I just wanted to mention that there are also some really promising new products that I think have great potential for retrofit situations and sort of in-unit solutions. So these are, again, going back to sort of a unitary approach where you don't have an outdoor unit. So this is an example of a heat pump that would mount on inside, but against an exterior wall. And then all you need to do is have sort of 2 6-inch openings, and then everything happens within that box. These units do tend to be more limited in terms of their capacity. So if you were to want to meet your full heating and cooling demand, you may need to have some improvements to your enclosure, or maybe you need more than 1 unit. So you definitely have to consider the capacity. The other neat thing is that there are options like this unit as well that you can add heat recovery ventilation. So like this mini split unit, it's not providing any outdoor air. So if you have ventilation issues, it's not going to solve that. All it does is recirculate the air that's in your suite and condition it to the temperature that you want. Whereas a unit like this is capable of actually bringing in filtered outdoor air and then exhausting it and recovering the heat to preheat the incoming air. So it's pretty slick, very efficient. So they're capable of very high level of performance. But once again, they are like smaller capacity units. And then this is just an example of the same idea, but a ducted system, which can be more challenging for existing building retrofits, but not impossible. So that's just to kind of put out there that there are a number of sort of new options that I think are really well suited to retrofit situations. Okay, and then we have what we call central heat pumps. So these 2 on the left, these are kind of like the mini split idea. So it's a split system where you've got your outdoor unit and your indoor unit, but they're designed for slightly bigger systems. So this is the kind of system you would see maybe for a townhouse strata or a single family home. So it's the same idea, just slightly bigger. And they're typically used for like furnace replacements where you already have a ducting system. You take out the like the natural gas furnace, you put in this heat pump, the indoor unit just connects in with the ductwork that's already there inside and distributes the same way that the furnace would have. This green one here is an example of a rooftop heat pump unit. So this could be a great option for any stratas that are looking to replace their makeup air units. Many makeup air units that are providing air to your corridors, they might have a heating element to temper the air going in the winter. Not many of them have any sort of cooling. Some of them aren't conditioned at all. They're just dumping air into the corridor to pressurize the corridors. So this can be a really nice way to maybe provide some relief if your makeup air unit is due for renewal, and just add a little bit more functionality to that system. And then this one is another example of basically it's like these central systems, but kind of sized up again. So this is a sort of system that might be used on a much larger building that has a central heat pump system. I would say more typically seen on new construction, because to retrofit something like this into an existing building, you've got to find a way. These normally would sit on like a rooftop, and then you've got to find a way to get all the piping through the building and then distribute either chilled water or refrigerant to all the fan coil units inside. So those exist, but I would say a more challenging solution for retrofits. And then I just wanted to show a few images of sort of the indoor unit options. So for any system that has an outdoor unit and indoor units, there's a range of options. Every brand has a slightly different version. This is like the cassette style indoor unit that's paired with typically mini split systems. And again, the designs change a little bit, but same general idea. They're often mounted fairly high on the wall. It's pulling return air in the top, passing it over the coil with a fan, and then it's blowing it out here. It's got some vanes to sort of modulate, and you can kind of turn it up or down depending on how much airflow you want. And these are kind of a similar idea, except they're designed to work in a drop ceiling. So if you already have a ducted air system, you might see something like this, or if you have very high ceilings and you have the ability to install bulkheads, you might use this sort of thing. So they're kind of less obtrusive if you already have the drop ceiling that you can nestle them into. Okay, and I'm turning it back over to Grant.
Now that we have a better understanding of what the heat pump is, and what the options are, the various types of heat pumps, now it's time to look at it from the council's point of view. What happens when an owner comes to them and says, well, I'd like to have a heat pump, I'm going to be installing it, yada, yada, yada. What are the sorts of things that stratas need to consider in terms of their responsibilities as for the corporation? One of the key things is that they want to maintain the quality and performance of the building's common assets. And those include things like the walls, the windows, doors, all the things that Strata is responsible to maintain and repair. And installing a heat pump has implications. The refrigerant lines are going to have to go through the walls. So how is that wall penetration going to be handled? Is it going to is the building enclosure going to be compromised? What about the balconies? If the unit's sitting on the balcony, will the mounting brackets for the heat pump be going through the balcony membrane and potentially compromising the waterproofing of the balcony? So there's various aspects to the installation of a heat pump system that will affect common property, and the council needs to be aware of this and have a strategy in order to address this. Another issue would be the adequate structural support for the units. In most cases, for these smaller units, for individual units, for owners, it's probably not a concern, though it might be if they want to mount it on a wall, or if it's a really old balcony that may have inadequate structural capacity. More a case in if you're doing a large rooftop unit, you want to make sure your roof can support the loads. And there are potentially building code issues. One key one would be the proximity of the unit to a guardrail that may present a climbing hazard. And if it's within a certain distance of that guardrail, code issues come into play. And then there are actually aesthetic considerations as well. I mean, looking at this image, all of the heat pump units are in the same location, the same size, the same look. It looks well considered, thoughtful, and coherent, rather than having different types of units in different locations scattered, some on the wall, some in different locations on the balcony. That affects the appearance of the building, which actually has an effect on the value of the property. And you also want to be considering even just coordinating things like where the electrical, refrigerant, and condensate lines are located and configured.
So some other considerations, electrical service capacity. So, you know, if everybody in your building added a heat pump, can the in-suite panels handle it, and can the building as a whole handle the load? And I would just suggest that it would be prudent to have an electrical contractor do an evaluation for your building, just so you know the answer to that question before you get too far down the road. I will say that, you know, if you're starting at a point where you have electric baseboard heating, And if you have electric resistance domestic hot water, you probably have more capacity than if you have a gas heated system, but regardless, it's a good idea to have that evaluation done up front. And the other point I want to make here is that the heat pump options that are allowed or selected can also have an impact on upgrade requirements. As one example, my brother just recently replaced his oil furnace with a heat pump, and the installing contractor gave him two options. He said, okay, you can do this one that you originally selected that's a little bit less efficient, a little bit cheaper, but then you're gonna have to pay for a panel upgrade. Or you can select a slightly more expensive heat pump that's more efficient and doesn't require the panel upgrade. The net cost was about the same, but I would say that the hassle factor might have been less with going with the slightly more expensive unit that didn't require the upgrade. So that's just to say that the heat pumps that are selected or allowed can have an impact on the electrical requirements within the suites or within the building as a whole. And then I want to talk about energy performance and acoustical considerations. So in terms of energy performance, I sort of alluded to this earlier. You know, the performance of a heat pump varies between makes and models, and nearly pretty much every heat pump, the efficiency degrades at lower temperatures. There are products that degrade less at lower temperatures, but it's not uncommon to see that COP drop to 1, which is essentially the same as electric resistance at temperatures below 0. So if, you know, as a strata, you have any sort of commitments or goals around energy efficiency, you might want to set some standards around some minimum performance. Certainly if you're accessing incentives, the incentives have minimum performance requirements. And then to also think about the impact on utility costs. If you're heating by electric baseboard already and you're installing a heat pump that can offset some of that heating demand or most of it in the winter, as well as providing cooling in the summer, there's a good chance you're going to be saving utility costs. If you were to just add a window unit, no change to anything else, guaranteed you're going to be paying more for utilities. So I think condo owners need to have a basic understanding of how their utility bills might change and how their choices could impact that change in their utility costs. The way, and I'll just serve as a side note, the way the units are controlled can also have an impact. In one of the studies we did, we found that the way a heat pump was set up, this is in a colder interior BC climate, a central unit. The heat pump was actually switching off at 5 degrees Celsius and switching to electric resistance backup heating. And that's just the way the controls were set up. So that's another thing that I think you'll want to pay attention to if you are installing it, to make sure that they're set up to kind of operate through their full range of capability. So in terms of energy performance metrics, I did want to give a really quick lesson here. We've talked about COP, and I think COP makes intuitive sense. So that's referring to the overall efficiency of the unit. So heat delivered or removed from the indoor environment divided by the power consumed. Consistent units, you're likely to see anything between 1 and 4.5 for most products that are available. EnerGuide, you can see the snapshot here, as well as utility programs have requirements around seasonal energy efficiency ratio and heating seasonal performance factor. So those are similar in that they're, again, reporting on energy removed or added divided by energy required, but they have a funny kind of mixed units. So the range of numbers looks different than sort of the COP. So just to be aware that just sort of the scale is a little bit different on those factors, but it's good to have sort of just a general understanding so that you can kind of compare products. I also want to just mention a few resources that are available. So if a strata or strata council does want to set some performance requirements, maybe within their strata bylaws, on what types of systems are allowable, there are some resources out there to help with that. So the Air Conditioning, Heating, and Refrigeration Institute, or AHRI, directory is the most comprehensive listing of heat pump products in North America. Basically, AHRI sets a standard for testing heat pumps, and any product that has been tested in this consistent way is listed in the directory. So, and pretty much every product has done that. The one downside to this listing is that it's massive. There's tens of thousands of maybe hundreds of thousands of products listed on it. It doesn't tell you whether a product is available in BC. So there are a couple of other product listings that help you kind of zoom in. So any sort of incentive program or incentivized models do need to be on BC Hydro or Fortis's qualified product listing. And that's basically a subset of the AHR directory that's been filtered for the minimum seasonal heating performance factors that the incentive programs have set. Then there's a consortium of energy efficiency directory, which again is a subset of AHRI, but they set as a minimum Energy Star's minimum requirements are better. So these are kind of the better performing to best performing units that you can get on the market. So if you are a strata that's wanting to support and promote the best performing units, this could be a great place to start. And then I just wanted to throw in one more for people who want to really kind of dive into the more technical details. The Northeast Energy Partnership provides a broader range of performance data that's more suited to cold climates. And by their definition, where we live is actually a cold climate. So the AHRI standard has sort of sets temperatures at which you have to test, and they're actually fairly high temperatures. And there are products that are specifically designed to perform well at low temperatures. And so this is a great resource for those higher performing units. And the units that perform well at low temperatures tend to also perform well overall. So I want to touch on sound. So sound is a really important consideration for strata councils and strata owners, where especially stratas that are, apartment style in a single building, you might have balconies right next to one another. And the sound levels of heat pumps can vary quite widely. And sound data is not readily reported. So with all these directories, you can kind of do a filter sort for whatever, like the capacities you want, the efficiency you want, and get a nice like table of available products that qualify. None of those listings include sound data at that level. So what you need to do is kind of filter for the products that you think are appropriate or that are on the BC Hydro list or the CE directory, whatever. And then you take the model number, do a Google search, find the performance data for that specific product, and then most will report on their sound data. So the noise levels of this particular one, I just did an example. So I'm like, okay, I like the efficiency, the capacity is about right. Noise levels are in the 40s decibels. So what does that mean? These are, I think, pretty quiet units. A fridge, it's within the range of what a fridge operates at. So you kind of hear a low hum. I have a heat pump system in my house and it's rated at 38 decibels. And if I'm walking by and it's on, yeah, you can hear a low hum, but it's not particularly loud. You wouldn't hear it on the next door property. Versus another neighbor's unit is definitely a less efficient unit. And when that thing turns on, it sounds like a jet engine. So the sound levels can be up into the 70s. So it's definitely something that you want to pay attention to and possibly set some parameters around as a strata council. Okay, and back over to Grant.
There are some larger issues that councils may want to be considering in terms of adapting their buildings to changing climate. One is that building systems work together. One asset, and I'm using depreciation report terminology here. I'm thinking of all the different parts of the building. or the responsibility of the strata to maintain and repair. And that might be the electrical and mechanical system components, landscaping, elevators, windows, etc. All of those things that need to be maintained and repaired. They all work together to perform optimally. So in terms of your renewing assets, replacing assets in your mechanical, electrical, and building enclosure systems, how do you take best advantage of that in preparing your building for climate change? So that might be setting comfort and performance targets, and then planning for the asset replacements to help contribute to meeting those targets. So selecting a window that's going to provide a certain degree of attenuation to solar heat gain, planning to reduce the need for cooling, and the consideration of using other passive cooling measures in controlling heat gain in your building. Also, you want to be considering the timing of things. When are your assets coming to the end of their service lives? Is there a building enclosure project upcoming? Is there a need for upgrading your air handling? When this is done is important. So if you're making improvements to your building enclosure, that might reduce the need for the loads on your air handling. And understanding the sequence of things and how they interrelate is important in planning your renewals and replacements. And then, of course, if you have a plan to upgrade your building and you want to meet a particular performance target, it's important to know, have a good idea how much that's going to cost, how much you need to put away in your contingency reserve fund, how large those special assessments may be. And then the owners as a whole need to understand why this might be a good thing to do, and to have their buy-in so that you can carry it out over the long term. And of course, there's legal considerations which go well beyond our expertise, but I understand there's a future webinar which we will be dealing with some of these things. So let's look at this, an example of different things that can keep your building cool, looking at the building as a whole. So again, we're dealing with incoming solar radiation. So one of the first things you can do, or one thing that you can do, is upgrading the windows. And what does that mean? That means windows that have reflective coatings and control solar heat gain. Tinted glass can do that as well. And triple glazing or better insulating windows will also control both heat gain and heat loss. Another really simple way of controlling heat gain is the use of shading devices. And those range from everything from awnings to shutters, and maybe even more interesting, landscaping. Consider a deciduous tree outside your window. In the summertime, it provides lovely shade. You can have a nice view of a leafy tree. And then in the wintertime, the leaves fall off, and when the sun's lower on the horizon, it shines. You get nice sunshine during the wintertime. Well, whenever we do get sunshine here on the West Coast. And then there's adding insulation to the walls and the windows. Again, that'll reduce the amount of heat that's conducted through the wall from the outside and from the inside during the winter, and help control temperatures inside your building. So this all involves controlling the overall performance of your building enclosure. All the things that you do will affect the amount of cooling that's needed during the summertime and heating during the winter. And there's lots of examples of really interesting ways of providing passive shading on buildings. Some of them quite traditional, the old-fashioned shutters and cloth awnings, to much more architectural and elaborate means, as you can see in these illustrations. And you can have a lot of fun with this, or just go with really simple means.
Thanks, Grant. So we're going to geek out for a minute here. And I really want to share some of the research work we've done because it's quite striking. So this was some work we did for the University of British Columbia on looking at ways to reduce overheating in various types of multifamily buildings. So what we did was we took sort of your typical a 4-story multifamily building, maybe built in the 1970s or 80s. It probably has double paned, non-thermally broken aluminum windows, probably overheating. And so what we did is we create a digital model of that building, and then we test it in some different scenarios. So first what we did was we put that building into a 2050s climate, which actually was not that different from what we experienced last summer. So not entirely unrealistic. And we modeled the number of overheated hours in the warmest suite. And what we mean by overheated hours, it's kind of a, it's sort of an engineering standard for acceptable temperature. And it basically says, you know, most people are okay if the temperature is at this or lower. And so in July, that temperature is 28 degrees Celsius. So any hour that's above 28 degrees Celsius in July is considered an overheated hour. Now, you know, last summer we had, in my house, we had a few days in a row where it was about 28 degrees Celsius. And I personally found that quite uncomfortable, difficult to sleep. So if anything, this is maybe understating the impact. And I think most people would be wanting something a bit cooler, ideally. So when we put this building, again, this building has no mechanical cooling. It just has, like, you know, manually operated bathroom and kitchen fans, and you open your windows for ventilation. So when we model this building, we find that in the warmest suite, they have nearly 800 hours above 28 degrees Celsius, or overheating hours. So if you experience that all at once, that's like over a month of very warm temperatures, which is probably unacceptable to pretty much anybody. So then what we did was we tested some strategies to manage the solar gains and limit that overheating. And this is what we find. So here's your baseline again. So again, your typical sort of existing building. And then we added operable shades. So that could be anything it's on the outside of the window, and something that you can control and block the solar gain when you need to. Pretty dramatic reduction in overheating hours. So a very, very effective measure. Now, there are some implications to sort of views and daylighting and that sort of thing, but we're just looking at sort of mitigating solar gain here. Fixed shading is also very effective, slightly less so than operable, because this is like, you know, like an overhang that's fixed. So you're not able to control all of the sort of solar angles. So you do still get some direct solar gain. Reduced solar heat gain coefficient glazing. So this is glazing that has a coating applied that reflects more of the sun away, so that you get less of the direct solar gain coming in through the glass. Also very effective. And as Grant alluded to in his previous slide, even just if you're replacing your windows and you go with a better insulated option with better insulated frames and glazing, that also has a beneficial impact. So really, you know, anything you can do, doesn't have to be a high-tech solution. Anything to block solar gain before it comes into your suite will be extremely beneficial. It will limit the increase in temperature to begin with. And also critically, it will delay an increase in temperature, which from a grid perspective is really important. From what I've heard from BC Hydro, they have plenty of sort of overall capacity for the next couple decades. But if everyone installs air conditioning and turns it on at 4 p.m. on the hottest day of the year, we're likely going to have some problems. So further to that, we did another neat bit of analysis that I think is also very striking. Looking at what we call passive survivability, which is sort of looking at how our homes protect us in extreme events where we lose power. So if you lost power in the winter, how long can you safely inhabit your home before the temperature drops too low and you have to leave? In the summer, same thing. Like, how long will your building kind of maintain a tolerable temperature without any sort of intervention? So again, it's going back to the benefit of sort of passive solar control. So this is, again, sort of a modeling exercise where we simulated, in this case, it was a new high-rise building that has mechanical cooling. So maybe there's already mini split heat pumps in every suite, for example, but nothing really deliberate was done to manage solar gains passively. So what you're seeing here is, this is the hottest week of the year based on 2050's climate again. So the dotted line is the outdoor air temperature. And then this blue line is how the building's performing kind of as designed with the cooling system working. So as expected, the cooling system was designed to work in these scenarios. So you're kind of chugging along sort of, between 24 and 26.5 degrees, everyone's happy. Well, let's imagine now that there was a wildfire event and the wildfire took out some major transformers and the same building is now without power during that same week. This is what happens to the interior temperature, the perceived interior temperature. So really, and it's particularly pronounced in a high-rise building because the high-rise residential buildings tend to have a higher percentage of glazing compared to opaque units. And the glazing is the primary way that the solar gain comes in. So you're actually getting temperatures inside that are even higher than outside temperature, and you can't get it out. So these are sort of veering on. These were really temperatures that we actually saw this summer and getting to dangerous levels where life safety is actually in play. So then what we did was we said, okay, well, let's take the same building. We're going to add some operable exterior shades. So again, something on the outside that you can control and block the solar gain before it comes in. And we also modified the glazing to have the low solar heat gain coefficient coating on it. And this is what we get. So again, power's out, and the orange line is kind of how that building is performing. So it actually does really well in that scenario. And again, I've just thrown that sort of red line is like that 28 degrees, like the engineering sort of acceptability limit, just as a reference point. Back over to you, Grant.
So as you can see from the previous slides, controlling heat isn't just about installation of heat pumps. And in reality, climate change isn't just about hot air. It's about other things as well. It's smoke from wildfires affecting air quality, power outages during more frequent, more severe storms, heavier rains. All of these things affect the durability, livability, comfort, and power usage of your building. Consider that as we increase the use of mechanical cooling, more electric vehicles, and mechanical air supply, there'll be more power usage. And it's going to affect the value of your property. And so you need to be considering, I think, it would be advisable to consider not just addressing specific problems through specific solutions like using heat pumps. There's lots of ways of addressing heat gain in the building, and considering the whole building as a system is really important, because many of the maintenance, repairs, and renewals that you'll be carrying out over the future are opportunities to address all of these issues and some of them together. And key to this is recognizing that your assets are going to be in place likely for decades. So at some point in the life of your building, you're going to need to replace windows. Those windows are going to be there probably for 30, 40, 50 years. And they're going to have to perform in a changing climate. How they may perform well now, but how are they going to perform 10 years from now, 20 years from now? How is that going to affect the comfort of the occupant of that space 20, 30, 40 years from now? How is it going to affect the perceived value of that property in the future if it's a property that's a suite that is known to overheat? It's important to consider the lifespan of those building components in the context of a changing climate. So adaptation to climate change can be a part of asset planning. You want to be considering how your new assets are going to work together, how your windows are going to affect the performance, the need for cooling in the building, and sizing your cooling apparatus appropriately. Where are you going to get the most bang for the buck? Is it through installing a heat pump, or is it by putting an awning over your window? And you want to be considering changing codes and the changing expectations about comfort. Changing codes are requiring higher performing buildings that will create a different sense of what can be expected in terms of building comfort. And that's going to affect people's perception about what they want to be living in. Do I want to live in a building that's comfortable because it meets higher performance value? Or do I want to live in a building that overheats? You also want to be considering how things get built. There is probably an optimal way of scheduling replacements and renewals, when to do which projects, and how to do it in a way that minimizes disruption to the owners. So what you want is a plan. And something as simple, that plan might include something as simple as the bulk purchase of bamboo exterior window shades as a temporary but effective measure to reduce solar heat gain.
Thanks, Grant. Yeah, so we're wrapping up now, and I think Grant and I are happy to stay a little bit beyond 10 to take some questions. I just wanted to kind of close out by sharing sort of an example of, this is something that we're working on at RDH, and sort of folding in some of these considerations into how we do our depreciation reports. So I just wanted to share sort of what that can look like, and maybe some of the questions that you might ask your depreciation report provider, because it is it's a tool that already exists that allows you to project into the future and plan, sort of do financial planning. And with a few modifications, I think it could be a much more robust tool. So just as a couple of examples, I alluded to earlier the Clean BC requirement for all new heating and domestic hot water equipment to be minimum 100% efficient by 2030. So here in this particular plan, you've got domestic hot water assets due for renewal in 2022. I think just being aware of this coming may sort of influence what you want to do in the coming years around domestic hot water equipment. And as Grant already touched on, you've got your windows coming up in 2023. Those are going to be in place for the next 25, 30, 40 years. So making choices about those windows that don't even necessarily have to cost more, but just think about future conditions. So the lower solar heat gain coefficient glazing is actually a very low cost item that can have a very beneficial impact. So just thinking about that is really key. And then there's the opportunity to add things that are maybe not current assets, but will be assets in the future. So adding heat pumps, for example. You can, maybe the depreciation reports are an opportunity to do some financial planning around that addition in a coordinated way. Cooling, maybe even shading apparatuses, that sort of thing.
So in summary, there's some key takeaways that we'd like to summarize. First of all, cooling demand is going to increase as our climate warms. And in considering installing heat, for instance, heat pumps, you need to have guidelines to ensure that your common property isn't compromised. And it provides a consistent, transparent, and fair process for approving these sorts of things. Also, mechanical cooling, heat pumps, for instance, is one component of a broader approach to climate adaptation. So consider passive means for controlling heat gain and to reduce the need for mechanical cooling. And integrate climate adaptation into your long-term maintenance and renewals planning. Consider the whole building and asset building system relationships as you're doing that. And really, in the end of it, have a plan so that you have a target and a way of getting there. Thanks very much.